Normal approximation to a binomial is our new topic we are going to see in this lesson. Please don't forget to subscribe to the channel. Now, what happens with normal approximation to a binomial? We know what a binomial is, and now we know what a normal distribution is. Now, under certain conditions, a normal approximation and normal distribution can be used as an approximation to a binomial. Now, under which condition? Now we know in binomial we are using the number of trials, but the highest number of trials we saw were up to 20. Now, what happens if I do more than 20 trials, like 30, 40, and so on? The binomial can't work for us. So then we go to, because the values of the probability of success will be very small there, and some started in that table, that some even are not existing. So there we shall approximate that binomial to a normal. How do we do that? We do that if n is greater than 20, i.e. when n is large, the number of trials are large, and as p goes far from 0.5. We recall that if x follows a binomial distribution with the number of trials n and the probability of success p, we say that the mean there, or the expectation, was given by np, and our variance was given by npq. And remember that sigma squared, or the standard deviation, was given by root npq, and we said our sigma squared and square both sides is equal to this, and so that this is our variance from here. So always our variance is equal to sigma squared. And we have seen that if x is following a normal distribution, it follows it with mean, mu, and variance. So if we have our mean here, now if we approximate it to binomial, our mean is going to be np, and then our variance, our var is going to be npq. So whenever you see this, this will tell you that this is a normal approximation to a binomial. Now, there is a problem there. We know that a binomial is a discrete random variable, and then a normal distribution is a continuous random variable. How can the values of x work in the value of x in a discrete work in the values work in continuous? So that one, we do a certain continuity declaration. So we do that by either adding or subtracting 0.5 depending on the cases we are adding. So because the binomial is a discrete and a normal distribution is a continuous random variable, we do a continuity correction to compensate the change from a discrete to a continuous value. So what we do is to make these values from a discrete to a continuous random value, as you are going to see. So if we have x equaling to a, if you want the probability of x equaling to a, now this one, remember in binomial we said that every value of x has its own probability. But in continuous, we say certain values of x have their probability in a given range. So that's why we always convert them to these things here. So when x is equal to a, we say this is the exact probabilities. Now in normal, we are going to convert it in. We subtract a 0.5 less x, we add 0.5. When I have x greater than a, I add 0.5 on it. Now this will be how I write it in the normal. When I have x greater or equal to a, when I have greater or equal to a, this time round I subtract. When I have less than a, I subtract. When I have less or equal to a, I add. When I have, remember we said x greater than a, we add 0.5. Less than b, we have seen whenever it's less, we subtract. That's why you see it here. Greater or equal to a, we subtract. Less or equal to b, we add, as you see it here. So that's what we are doing here. So as simple as that. So that's how we do the continuity correction. Now, if x now follows is a normal approximation to a binomial, this one is the form. It means that now our from, I think you know how we are writing ours. It's going to be x now plus or minus, remember having here mean, mu, and then over sigma. Our sigma here is root npq. So this is now how we convert, how we standardize our x in normal approximation binomial. So now this is the way we standardize it. You know when we had only mu and sigma, we have just x minus mu over sigma. But here our sigma is this, then our mu is this, because now it's an approximation to a binomial. So let us see if we are given these examples. What happens if you now want to make these probabilities now in terms? So now these are discrete. Now you want to convert it to continuous. So what we say, this is the case we have here. We subtract 0.5 from this, and then we add 0.5 on the upper. So this will be in continuous, this will be probability of now subtract 0.5, add 0.5. Now this one, it's greater than 3. So if it's greater than 3, what happens? We add a 0.3. We are adding a 0.3. It's greater. Greater or equal to, we subtract. Now we subtract here 0.5, we get 3.5. Now we have less. We said when we have less, we subtract 0.5. So this will be the probability of x less than now 8.5. This is the case we are having. When we have less, we subtract from that value, we subtract 0.5. Now this will be, we have less or equal to. Now if we have less or equal to, we just add 0.5. Probability of x less or equal to. When we add 0.5 here, we get 5.5. When you count this, we have now greater than 2. We said if it's greater than 2, we add 0.5. So we have that less x, less. When it's less, subtract 0.5 from it. When you subtract 0.5 here, you get 3.5. When you have now this, it's greater. When you say this is greater, we subtract. Greater or equal to, we subtract 0.5 to come to this, less or equal to x, less or equal to, and on this we add 0.5 because it's less or equal to. So whenever it's less or equal to, we add. Now what happens to this? This we have greater, so the greater we add, just in greater. So we have 1.5 less x, less, this one is less or equal to, we shall also add 0.5 to get 8.5. And then when you have this, it's greater or equal to, so we shall subtract from this, we shall get the probability of 1.5 less or equal to x, less, then we shall also subtract from this because it's just less to give us 4.5. So that's how we look at the continuity corrections in the numerical approximation to a binomial. So these are very crucial. Now we are going to see how the examples, how questions are going to be in the next lesson. See you there.